homework, and I guess this is really only for Nate, since he'll send them out to you. Last week it was the new 789 plus
7 through 12.
was the old 7 through 12, thank you. And today it's the old 34. And X and Y. Now this sounds absolutely like I'm trying to trick you. Basically, this is all on Nate's plate. And he's going to incorporate them into the exercise file that I began the semester with. And I'm not sure how you'll number them, and maybe in your email you should tell them what these translate into. Okay?
Yeah.
Am I clear?
What we've added 3 is an X and Y, so it's something that needed to be done.
So say that again?
We've added 3. And then
We've added 3,
X,
new 7, 8, 9,
so
and now there's the new 8, X and Y. But somehow put them in the right place in the list of exercises, and then tell me too.
We're at 34.
Right. But it's really, I mean, basically I'm doing it by the material we're covering right now. And what I've decided to do is, next week I'll have a regular lecture, but I thought it might be a good idea the week after that. We have a session which I just assume not to be filmed, if you don't mind, but just like a review of some of the functional analysis and some of the real variables some people might not be 100% up to stuff on, and to do problems. Okay, so you know, after 4 or 5 straight lectures, then we have a session where we do what I just said. What concepts aren't you comfortable with? And you're not shy. I mean, we're all God's children here. Not everyone, no one knows everything. So, and then mess around with some of the problems. Okay, so last time I ended the lecture by telling you this famous theorem of Bill-Bashi's. And it, I guess it's okay to repeat, it said that if R is bigger than or equal to 1, then there exists a function psi, which is R times continuously differentiable against compact support on the real line such that psi m n is m and n ranged through all the integers. Is an orthonormal basis for L2 of R. And that result is difficult, and it's juxtaposed with the fact that what Haar did, properly modified to R, was not smooth. He had constructed a Wavelet basis way back in 1909, 1910 in his thesis, but it was essentially step-type functions, which we'll go into in quite some detail. So that was a significant step forward. And believe it or not, smoothness, even though you have to digitize everything, is relevant for lots of applications, especially in image processing. So it is not just a mathematical result, although it's a beautiful mathematical. It's interesting that prior to that, the hi, who are you?
Oh, sorry, I'm from Technology Service Corporation.
Oh, you are? Oh,
yeah, I just wanted to audit your class if it's okay.
Sure. You can pay me afterwards, so
okay.
So you don't pay the university anything, but we'll set up a
This is on tape, Professor.
It's okay if you guys are complaining.
wavelet theory, Yves Meyer actually constructed functions that were in Schwarz's S-class, so they're infinitely differentiable, and they decrease to zero faster than any polynomial for each derivative, which he dilates and translates for an orthonormal basis. And their Fourier transforms were compactly supported. But that's different. This is if you actually construct the wavelet itself that way, this was basically a new result. But both results were spectacular. It's just that one wanted to know this in light of the Haar field. Well, and just so you, the wavelet system is basically 2 to the m over 2 psi of 2 to the m t minus n, where m and n. All right. Well, the next step in all of this that happened was essentially the evolution of the idea of multi-resolution. We talked about that last time also a little bit, indicating these pyramidal schemes that rose in the early 80s with people like Burt and Adelson in image processing. And these coupled with ideas from speech, with quadrature filters and the like, that led to full-blown wavelet theory, and in the form of multi-resolution analysis. And one of the things one wants to keep in mind, especially since when wavelet theory first began, people thought it might be a replacement for sliced bread in its grandeur, is that I think most of us realize now that it's several beautiful techniques, by the way, quite broad in its applicability, but it's really, it solves a certain type of problem, or it's relevant for a certain type of problem in the applied arena. The mathematics is another matter. It's a beautiful theory that is still expanding, but it's not, doesn't have the catholicity that one might have originally thought. It certainly doesn't meet the uncertainty principle and that sort of thing. In any case, before I give a formal definition of multi-resolution analysis, let's just give an intuitive definition. And basically, what one does is one sets, so set f cap m equal to the sum m less than or equal to cap m, the sum over all n integers of the inner products f psi m n, then psi m n, where we assume, just for this illustration, where for this example, assume the wavelet psi satisfies the property that the support of the psi is contained in a nice fixed interval minus a half to a half. Certainly do that. Well, if you do that, and I leave this as a calculation that you should do yourself, if you do that, then this implies, then, you do the arithmetic, and it's strictly arithmetic, the support of psi m n is contained where? I mean, we're assuming that's contained in there, and so when you define psi m n in this way, the support of psi m n, that is to say, the support is the smallest closed set outside of which this is equal to 0. This is contained in IMN. We're going to be looking at these sets very closely in a week or so, but right now let me just blurt it out what it is. This is equal to the closed set n 2 to the minus m plus 2 to the minus m plus 1. And then I'm going to go, excuse me, I'm going to do just a minus. And then it's going to be n 2 to the minus m plus 2 to the minus m plus 1. So you see what's going on is by doing these dilations and translations, the original support is being spread around in a very well-defined way. As I mentioned last time, these dilations and translations are associated with the so-called AX plus B group. And now, instead of being centered at the origin, it's centered at the point n over 2 to the m. And instead of having a radius of a half about the origin, its radius about this point n over 2 to the m is 2 to the minus m plus 1. So remember last time, before I stated Debouchy's theorem, I showed you one of the nice properties of wavelets, namely this localization property. I don't know when I board there, I said that one of the weaknesses may be of Fourier analysis, if you want localization. Fourier analysis doesn't give you that, not really. One of the weaknesses is that if you adjust your signal just a little tiny bit, then all the Fourier coefficients vary. And what you'd like is a theory where if you adjust your signal just a little bit, then maybe just a small family of coefficients change related to that adjustment. And wavelets do that, whereas Fourier analysis doesn't do it. And so that I showed you that by example last time. Well, here, if we're going to have a wavelet decomposition, that means the wavelet decomposition of a function f. Let's forget that m there. You're going to have f equals this double sum over all the lens and all the lens. That's what a wavelet decomposition of that function f would be. But here, I'm writing down just one of the approximates. I'm looking at all the n's, with only the m's less than this cap m. And what does that tell us? Well, what that tells us is, well, first of all, the measure of this set, the length of this set, is what? The length of this set is 2 to the minus m. Okay. And so, if I look at now f half m plus 1, what is that equal to? Well, that's equal to f half m plus the sum over all n of f psi half m plus 1 summer n psi half m plus 1 comma n. I'm afraid my m's and n's all look the same. That's a capital M, that's a lowercase n. Capital M, lowercase n. And so what does this mean? Well, what this means is that this, let me use suggestive language, deblurs Fm by adding to Fm the behavior of f on intervals of length 2 to the minus m plus 1 on intervals of length 2 to the m plus 1. And so that's a very interesting feature of wavelets. And that's a feature which can be reinterpreted as a technique to decide when to stop zooming in or zooming out. I mean, when you go on MapQuest or something like that, you're allowed to zoom in and zoom out. And sometimes you don't have to zoom in all the way down to the grass on a guy's lawn. You just want to know what street he's on. And so, similarly, if you have expenses, whether it's a time expense or it could be a money expense or some sort of expense associated with an experiment you're doing, once you get your information, you can stop your zooming in. And that's what this tells you. And so in that sense, wavelet theory is very convenient if you don't need detail beyond a certain level of what you want to know. Okay, so this setup led to a notion which is called a multi-resolution analysis, and I'll just call it an MRA, multi-resolution analysis. So I'm going to write down a formal definition. And basically the idea really was in the works a long time, in the late 70s in the speech community, the quadrature mirror filters, as I'm repeating myself, I know, but, and in the vision community in the early 80s. But it was formulated first by Yves Meyer, as far as I can tell. And there's a lovely paper by MAIT in the transactions of the AMS, also during that period. And basically it's the following. So Vj phi is an MRA of L2 of R in this one. If the following holds. Each Vj is a closed subspace of L2 of R. Each Vj is contained in Vj plus 1. The union of the Vj's, when you close it up, is equal to all of L2 of R. And the intersection of the Vj's is equal to the zero function. And it has this dilation property that f of t in Vj holds if and only if f of 2t belongs to Vj plus 1. And then the final property is, so it's definitely a property of this definition, but let me write it over here, is that f, well, I'm going to write it in 2 parts here. F belongs to V0 if and only if for all k, ta translation by the integer k of f belongs to V0. We've defined that before, right? And phi, this function phi, the first time we're mentioning it now, belongs to V0. And not only that, but, and it translates by integers of phi form an orthonormal basis for V0. Okay, so it might seem artificial. We've essentially put a structure on L2 of R, but it is motivated, highly motivated, by examples like this, and to try to give some mathematical modeling to L2 of R so one can analyze signals that are in finite energy. Well, this is the basic definition. Lots and lots and lots of things have been done on this. It's this original definition. We're going to talk about some of them in this course. It generalizes to a great extent, and we're going to talk about some of those things. But I just want to get the basic primordial definition down written carefully. Okay. Now, once you have an MRA, remember, we talked about orthonormal bases for L2. Well, just think of what was known. I mean, if you were just on L2 of 0, 1, then the exponentials, either the 2 pi I n gamma or t, form an exponential basis for L2 of 0, 1. If you go to R, the most natural one that existed for many, many years were the Hermite functions. And that's already complicated, and it doesn't have the structure one would like for generalization. It's a orthonormal basis, and people understood it would be pretty good because it has exponentials in it and polynomials that are going to make things die down, but it didn't have the structure that one would hope would give insight into the orthonormal basis itself and possibilities of generalization. And so when Dobachis and did this, and Meyer did his orthonormal bases, and they understood that there was some structure involved. And then the MAIT paper, which was inspired by Meyer, formulated this notion. This really was the groundwork for doing something much, much more explosive, expansive, and seeing that there was basically an infinitude of these guys with tremendous complexity and range. I mentioned the MAIT paper a couple of times, and I'm also saying Meyer did it, because Meyer wrote a paper that appeared in lecture notes in Torino from 1987, way before MAIT's paper. And he basically did all this. MAIT wrote down new things in his paper, but had the same notion of multi-resolution analysis. Now, what's an example of an MRA? And what good is an MRA? I've just said what it is, but let me be explicit now. An example is
question.
Phi equals, yeah?
I'm sorry to interrupt.
No, you ask questions.
The second property, is that they're nested going up, right?
Yeah. Oh, by the way, let me interrupt you for 1 second. Some Dobachis, who deserves to be listened to very carefully in this matter, since she's one of the originators of the subject, actually has the nesting going down. But most people have it going up, and I'm just going to follow that. But go ahead.
If it's nested going up, how can it intersect with 0?
Because think of them going down. I'm looking at the intersection. They're going to get smaller and smaller and smaller and smaller.
Where is V0?
It's in the middle. These are all the integers.
Oh, okay.
So V0 is right in the middle.
I thought you were right up.
Yeah.
Thank
Yeah,
you.
no, it goes down, V minus 1, V minus 2. Okay, good question. So phi, if you let it just be the characteristic function of the interval 0, 1, and then you define V0 to be equal to the closed linear span of these translates of phi. So that's an example of an MRA. That's not obvious that that's an MRA. Basically, there are things to be proven, lots of things to be proven. So first of all, you would define the VJs by this, okay? So that just becomes a definition. But then proving these properties, there are things to prove. It's not obvious. But this is an example. Now, why do we want MRAs? So let's go over here to answer that question. The reason we want MRAs is because there is basically a formulaic thing one can do, which people like me are understood early on, to make wavelets. That is to say, to construct functions psi whose dilates and translates are orthonormal bases for L2. Okay? And so the theorem is the following. And later in the course, I'm going to prove this in great detail, but I want to give you an idea of things so you can actually do problems. You can get involved in the Wavelet toolbox for some of the exercises we're handing out. You can see some of the usefulness in a concrete way, by my stating it now, but I also want to give you the mathematics behind it. Well, given an MRA Vj phi of L2 of R. There exists a constructible very important, it's not just existential, you actually make the function. There exists a constructible psi based on this MRA such that psi mn is an orthonormal basis for L2 of R. And I'm now going to tell you the algorithm to do that. I basically saw this first in Mayer, but Malak was Mayer's student and a very brilliant engineer, and Mayer's a very formidable and deep mathematician. And so from this vantage point of many years later, I don't want to take the risk of saying he did this and he did this. They certainly were very much involved in doing this material. So Mayer's algorithm for this theorem and I reiterate, I did say it last time, but besides the contributions of Doshi, Mayer, and Malak at this stage, if you recall, I emphasized that there were other groups in the world that were doing very similar things. These people, a lot of people were onto this. The Austrian group of Workenig and Feichinger, and the Americans, Yarwood from Sweden, Yarwood and Fraser. So this was in the air in some sense, but these people nailed it in a very clean way and followed it. So, so we're given an MRA, and therefore the translates by integers of phi form an orthonormal basis. And could one of you close that door? I appreciate that. Now, I'm going to go into definitions here carefully later on, but intuitively you know what this means. Let me just get away with it now. So Wj is going to be defined by a Vj direct sum Wj is equal to Vj plus 1. So that's a very feasible thing to do, because here we have, I don't want these things being equal. They are, we just get one. Make them look to the next one that's not equal. So Vj is contained properly in Vj plus 1. That is to say, I can look at its direct summed so that Vj sum something or other is equal to Vj plus 1. I'm calling it Wj. Now, what the algorithm says is the following. A, there exists a psi, it's really constructed, I'll show you how to construct it, in W0, such that tau k psi is an orthonormal basis for W0, and all of the dilates and translates form an orthonormal basis for L2 of R. So the point is to construct this function here, psi. And so we want to know, how do you do that? Well, how do we construct that function psi? Well, the way we do it is the following. There exists H0n complex numbers such that